Welcome back. In this video, we will continue to learn about ionic bonding. Specifically, we'll describe the octet rule and learn how to draw Lewis dot symbols for different elements. We'll also discuss how the position of a given element in the periodic table can be used to predict its charge. And then we'll learn how to match compounds' names to their molecular formulas. So earlier we learned about electron configurations and how we can have the expanded electron configuration or the noble gas electron configuration to describe elements. It's important to recognize that only the valence electrons of an element are involved in bonding. Therefore, the noble gas electron configuration, the one that has the noble gas core, the abbreviated version, shows to us the number of electrons that could be involved in bonding. Carbon, for example, has 4 valence electrons. There are 4 electrons in its outermost shell. Sulfur has 6 valence electrons. There are 6 in its outermost shell. And for main group elements, the number of valence electrons is equal to the group number. This allows for an easy way to determine how many electrons a given element has, and later we will see it helps us to determine the number of bonds that it likes to form. When we draw the Lewis dot structure of a given element, we put the atomic symbol and we surround it by dots equal to the number of valence electrons. Since carbon has 4 valence electrons, it has 4 dots. Since sulfur has 6 valence electrons, it has 6 dots. And it doesn't really matter where you put those dots around the elements. Some people like to have them nice and symmetrically arranged. For our purposes, we don't really care. Now, if you have an ion, as we talked about earlier, ions either gain or lose electrons. The reason this happens is because elements prefer to have a noble gas electron configuration. This is called the octet rule. So the octet rule describes how elements will either gain or lose electrons in order to have the same electron configuration as a noble gas. Sodium, for example, has the electron configuration 1s2, 2s2, 2p6, 3s1. That final electron in the valence shell of sodium will tend to get lost and given away to other elements, nonmetals specifically. In this case, we see chlorine is missing 1 valence electron in its outermost shell. So sodium can give its 1 electron to chlorine, and they both end up with the electron configuration of a noble gas. In the case for sodium, it ends up with neon's configuration. In the case of chlorine, it has argon's electron configuration. We can use the periodic table to help us know what charge a given element tends to make. You can see in this version of the periodic table, there are 2 numbering systems that are used. There's the A numbering system. We have 1A, 2A, 3A, 4A, 5A, 6, 7, and 8A. And those are the main group elements. It turns out that the number of the main group gives an indication of what common charge they have. For main group elements in 1A, because they have 1 valence electron, they tend to lose 1 valence electron, so they will have a positive charge of 1. Elements in the group 2A tend to lose 2 electrons and have a positive 2 charge. Group 3A is positive 3. We'll come back to group 4A in a minute. Group 5A elements, they tend to gain 3 electrons. And that's much easier for them than losing 5 electrons. It's easier to gain 3 than to lose 5 because there's a smaller transfer of electrons in this case. And so elements in the 5th group have -3 charge. In the 6th group, these are missing 2 electrons, so they gain 2 more to obtain a noble gas configuration. And then in the 7th group, these can gain 1 electron in order to obtain a noble gas configuration. In the 8th group, these elements already have a noble gas configuration, seeing that they are noble gases, and so they don't tend to gain or lose electrons. There's a couple other things here. Elements in the 4th group, these actually tend to not form ions when they are nonmetals. So carbon and silicon, germanium don't tend to form ions. The metals beneath them do form ions. And we'll notice something important here is that the transition metals are exceptions to the octet rule. They will lose electrons, seeing that they are metals, but they don't tend to lose electrons and end up with a noble gas electron configuration. The reason for this goes beyond the scope of this course, but you can learn about it if you'd like to in other courses. Now, ionic bonding occurs when ions combine to form compounds, and this ends up being a very favorable process because of the electrostatic interaction that occurs between different ions. We'll not say much more about this, but if you would like to learn more about this, you can study what is called lattice energy. The last thing to talk about here is about naming ionic compounds. The name of any ionic compound is obtained by combining the name of the metal with the nonmetal. For the metal, the cations, we will focus mainly on the group 1A, 2A metals, and aluminum. For all of these metals, the name of the metal is simply the name of the element. Sometimes you might hear it referred to as the metal plus the word ion. So lithium ion, calcium ion, etc. But in a compound, we simply use the name of the metal. For anions, there are monoatomic anions. These are elements that are just one, one element. These end in ide, so chloride, fluoride, iodide, oxide, sulfide, etc. So take any of the nonmetals on the right side of the periodic table, and they end up with an ide ending. There are also polyatomic ions. You can see a large list of polyatomic ions on the right. This includes ammonium, hydronium, sulfite, sulfate, nitrite, nitrate, etc. The ones that you need to know are the ammonium ion, the carbonate ion, the hydroxide ion, the nitrate ion, the phosphate ion, and the sulfate ion. So you need to know the names, the molecular formulas, and the charges associated with those ions, and therefore be able to determine what is the proper combination. So when we form ionic compounds, the charges of the cation must cancel out the charges of the anion. And there's a neat little trick to this. So if we have a cation, it's going to have a positive charge. Let's call this element X. Element X has some positive charge, and then it's combining with element Y, and it has some negative charge. In this case, let's say that element X has a positive 1, element Y has a positive or a negative 2 charge. In order to get the charges to balance properly, what you can do is you can crisscross the charge of each element and use that as the subscript in the compound. So this charge will go down here as the subscript, and this charge will go down here as the subscript. That would then give us X2Y as the formula for this compound. All right, let's go ahead and practice this. Which name and formula pair is not correct for these substances? Remember what we talked about. When you combine the ions, you need to crisscross the charges of those ions in order to get the proper number of each element in the compound. So pause the video and try this on your own. Welcome back. So let's work through each of these individually. For the first one, we have barium bromide. When you look at the periodic table, you see that barium is in group 2, so it has a positive 2 charge. Bromine is in group 7A, so it has a -1 charge. We have barium with a positive 2 charge, bromine with a -1 charge. So when we cross these, we would get 1 barium with 2 bromide. So that's correct. Aluminum and chloride. Aluminum is in group 3A, so it has a positive 3 charge. Chloride is in group 7A, it has a -1 charge. We cross those charges and we get 1 aluminum and 3 chlorine. So that is correct. Calcium carbonate. Calcium is in group 2A, so it has a positive 2 charge. Carbonate is a polyatomic ion, CO3, with a -2 charge. So when we cross those, we would end up with calcium 2, carbonate 2. However, anytime we have an ionic compound, we simplify whenever possible. And so this really simplifies down into calcium carbonate. Fourth one, sodium selenide. Sodium has a positive 1 charge. Selenide has a -2 charge, being in group 6A. So when we cross these, we get 2 sodium for every 1 selenium. So sodium selenide is not correct. Let's just look through E, magnesium oxide. Magnesium has a positive 2 charge. Oxygen has a -2 charge. So when those cross, we also end up with magnesium oxide. All right. One last word here, an important point to recognize is the use of these parentheses. When do you use them? If we have a polyatomic ion that is used, and there are multiple of those polyatomic ions, we need to use parentheses around the polyatomic ion group. For example, let's say that we had a combination of calcium and phosphate. Calcium is a positive 2 charge. Phosphate is a -3 charge. So when we cross them, we end up with 3 calcium and 2 phosphates. It must be written like this. That indicates that we have 2 phosphate groups. Without the parentheses, it would look like this. And now it is unclear. It makes it look like we have 42 oxygens as opposed to 2 phosphate groups. So that's it for this video. Thanks very much for watching. Have a great day.